The question here is saying we got cyclohexane, the methyl cyclohexane, and then the bromination reaction, right? It's BR2. So what happened was, sorry, what I forgot to put there is a light. If you can just get the bromine with the double bond, that's where the bromination reaction, Br goes this carbon, Br goes that carbon. That's the reaction we know it happens in the dark conditions. If you shine a light, then the bromine will break because it is a radical reaction. So bromine makes a radical, that's the initiation steps. And that is going to pick up the proton, hydrogen from the molecule. And which hydrogen is going to be pulled out? I hope that you don't pull the hydrogen from any of these carbon, right? This is a secondary carbon, that's a secondary carbon. But this hydrogen being more attractive because of this allylic hydrogen. But this molecule has 3 allylic hydrogens. One from there, one from here, one from here. Why the allylic hydrogens are better to abstract by the bromine radical? Because when you make a radical at that position, it's going to be the radical in the rational stabilized, right? So if the bromine take out that hydrogen there, then we're going to make the radical right at these positions. If the bromine pick out the hydrogen from these methyl groups right there, we're going to make a radical there. If the bromine pick out the hydrogen from this position, we're going to make a radical that position. These all 3 are the allylic radical. They are all resonance stabilized, right? So this one, basically the 1 electron from this double bond comes in, and then 1 electron from there make a double bonds, then leave that one radical goes to this point, right? That's resonance stabilizations. We can also draw the resonance structure of the other one, right? That one makes a radical resonance structures to make the radical go to this carbon right here. And this one, if a double bond comes in, the radical go to this position. So all 3 of them are the allylic radical resonance stabilized. Then we need to think about each one is going to pick up the bromine and it becomes a product. If that one pick up the bromine, then we're going to place a bromine right there. That's the product forms from that radical, that intermediates. That one, bromine come pick up the radical from there, then you're going to make this one. But if you look at carefully, these 2 is identical. These 2 are exactly the same. So either will basically make the same product. On the other hand, this the methyl radical, if you pick up the bromine, you're going to make the bromine goes to this methyl groups here. That one is going to make a different product. Bromine goes to that position. That's what it's going to be made from that radical. And then the last pair down there, if bromine is going to go to this position, you're going to make this bromine, allylic bromine products. And then that one, bromine goes there, at the tertiary carbon. So potentially we have a 1, 2, 3, 4, 5 products possibly formed from these reactions. And that was what we have discussed before. Yes, we did have, you were able to do this by following up, all the radicals and all the resonance structures, and then finding out what product they make. But now we can talk about which one's going to be major, which one's going to be minor at the given conditions. So let's compare the stability of the products and stability of the intermediates. So first of all, if you think about the stability of the product, then the more substitute double bonds becomes more stable. So let's look at, what type of double bond is this? This double bond is a 1, 2, 3 alkyl substituted, the tri-substituted double bonds. That one was a 1, 2, 3 carbon chain on double bonds, tri-substituted double bond. This one, on the other hand, just a 2 carbon chain, so di-substituted double bonds. And this one was a tri-substituted double bond. That one is di-substituted double bonds. So you see here, the double bond have a different number of the carbon substituents. If you do this reaction in the high temperatures, then the most stable product will be formed as a major product. It may not be the single one, but at least these 3 will be probably in as a majority. of the products. So these are the thermodynamic products I can expect if you do this reaction in high temperature. If you do this reaction at low temperatures, then now you should think about stability of intermediates. Then now we need to go back to radical, start comparing them. This is an allylic, everything's allylic. So allylic probably shouldn't even mention that. This is allylic and secondary, and these are the exact same things, so actually same structures. And that was an allylic and primary. That's an allylic and secondary, and this was allylic and secondary, and that one is an allylic and tertiary. So among them, which one is the most stable intermediate? You should be able to pick that one because that's an allylic and tertiary radical. That is the most stable intermediate. So if you do the reaction at low temperatures, is the reaction goes through producing the most stable intermediates and by making different things as a major product. So and then we call this a kinetic product, right? So now we can talk about a little more. As a major product, it may be more than one becomes a major, but at least we can figure out which one's going to be a major product, these three. But if you do it in the low temperatures, then it's going to just make a one molecule as a major. It's all because that's the one that goes through the most stable intermediates.